Okay, there we go. So, we said that we define a circle as the locus of points that are equidistant from some point, right? And so that gives us, if I were to take this point and just drag it around, you can see that it forms a circle. So, this is, remember this from last year, Geometer Sketchpad?
Yeah.
I'd like to have you guys do a little bit of stuff with that this year too. We'll see if we can work that in. Oh, how do I do that? I go. Gosh, how do you do that? Well, I can't see. I can't remember how to do this. There's supposed to be a way. I'll just trace. So anyway, you can see that makes a circle, right? Okay, no big deal. So I want to look at something different. Hal, I'd like phones away, please. I want to look at something different then. So let's look at a different kind of locus here. Let's look at a locus of points that are, they're going to be equidistant. Well, how do I say this? We want the set of points that are the same distance from a point and some line. Okay, we're going to call the point the focus, and we're going to call the line the directrix. Okay, what do you think that's going to look like? Oops, hang on a second. What do I have to do? Oh man, I messed this up. How did this go? Oh, I thought I had this thing built. All right. I just can't remember how I did this. No. Anyway, I can't remember. I think I messed this up. I'll fix this part of it. But here's what it ends up looking like, right? So we've got this focus and we've got this directrix. And if I want these two distances to always be the same to all of these points, right? So there's one example of a point, right? This is just, remember, these are congruent symbols. So we know that this segment is congruent to this segment. And then where's another obvious point that would be in this locus of points? If the distance from to the point, the set of points, each point in the set has to be equidistant from the focus and from the directrix. And keep in mind that if I want to talk about the distance between a point and a line, let's just take this point, for example, in the blue line. What can you tell me about the segment that describes the distance between the point and the line? How is it related to the line? It's got to be perpendicular, doesn't it? Right? It's got to be perpendicular. So this is always going to be, a right angle, isn't it? Okay. So there's one point in this set. The other ones we can sort of approximate, except for one. There's one that ought to be really obvious. That's the same distance, a point that's equidistant from the focus and the directrix. Where's it going to be? Yeah, right. It's going to be the midpoint of the segment connecting them, right? So there's going to be one for sure. Oh, there's one right there, isn't it? Right? Okay, because we can see that segment and that segment, those are going to be the same, right? Same length, so they're congruent. So what's that going to look like then? What do you think is going to happen as we get really far away? What's going to happen to these points? Like if I want to make these distances very large, on a very large scale, the focus and the directrix are going to look pretty close together, aren't they? Right? And so there's no way that this is going to describe a line that goes out like that, right? If everybody see that if we did that, it would end up being much closer to the directrix than the focus, right? So what do you think it's going to look like if we do this? Go ahead. Any ideas? Let's just maybe make one more point. Let's see, what if we went out some distance, like, let's say, oh, yay far, right? So then we could make kind of a circle there to define, right? It's not a very good circle, but you get the idea, right? Actually, I know what I can do. Hang on. I could do something like this. Oh, this would be tricky. So I could put one of them. Does that seem like that's about centered on the? Maybe I need to make it a little bigger. It's not quite big enough. Let's go like that. Okay. That seemed, sort of centered on that focus. Okay, so we've just got to take this one then and get this one so wherever they intersect, a vertical line is going to go through the center of the circle. So what do you think? Like, kind of right there-ish, something like that maybe. See what I'm getting at? So that point right there is going to be lined up vertically with the center of the circle. So you can kind of get an idea there, maybe a little bit, right? So this distance, in other words, when I just drew this distance right here, this is very imperfect, but that distance should be the same as that distance because the circles are just copies of each other, right? So what's this starting to do? It looks like to get from there to there to there, it must be curving a little bit, right? What do you think this shape's going to make, this locus of points? Yeah, it's going to make a parabola. Okay, so that's what it looks like, right? Well, let's look at the equations that we could get from this relationship and see if we can come up with an equation that represents all the points on the parabola then, right? So if we're going to label these points. If this one has coordinates, let's just conveniently, let's say that this point right here is the origin. And we can do that, by the way. This is called coordinate geometry, and it's easy. We can move things around and put them on the plane wherever we want to, wherever it's convenient. When we're doing a proof like this. So we're going to make this point the origin. Then we're going to make this point right here the focus. We'll say that distance is p, that vertical distance. And so we know then that the point directly opposite that, the focus, is going to have coordinates 0, -p, right? So the directrix would really be the line with what equation? Y equals what? -p. Okay, that's the equation of that line, right? We'll just say that this point up here, just the point that represents maybe the bead that's sliding on the wire, right, that forms the locus of all those points, its coordinates will just be x and y. Those need to be variable. And then whatever the coordinates are of this point, x, y, would you agree that down here then, if I were to go vertically down, the coordinates of that point on the directrix, it's immediately below it, are going to be x -p? Okay, so we should be able then to just set up an equation, right? We should be able to say that this distance and this distance have to always be the same. That's our only constraint, right? That's how we define the locus of points, is that those distances need to be equal. Well, how do we say a distance again? How are we going to define a distance? how do we define this distance? Let's say this distance right here. Let's just call it, for now, let's just call it D1. Oops. How do we define D1? Do you have to remember that fancy formula, the distance formula? You probably do. But what is the distance formula? It's just a Pythagorean theorem, right? Don't remember the distance formula because you're going to forget it. But it is just a right angle relationship, right? A right triangle relationship. Everybody see that? Just change in x and change in y are related by the Pythagorean theorem to the distance. So what's the distance going to be then? What's the change in x? What are the coordinates of that point right there? Well, that's 0p, and this what's the x coordinate of this one? Yeah. So then what's the difference? What's the change in x? That's 0, right? What's this? So what's the change in x? Okay. What if we start off with a value of 3 and we end up with a value of 7? What's the change in our values? How'd you get 4? 7 minus 3. So if we start off with an x value of 0 and we end up with an x value of x, what's our change in x? X minus 0 or x, right? Okay. So there's that part, right? So we know that x minus 0 is the change in x. What's the change in y? What are the coordinates right there? X is the x coordinate. What's the y coordinate? Gotta be p, doesn't it? Right. So then what's the change in y? Y minus p, right? And so change in x squared plus change in y squared must be d1 squared, right? So that distance must just be the square root of the sum of those squares, right? We all know that stuff. So we get the square root of x minus 0 squared plus y minus p squared, right? What about this other, let's look at the other one now. Let's look at this guy right here. What about that one? What's the change in x for that one? 0. Yeah, it doesn't move horizontally at all. Change in y is going to be what? Y minus negative p, which is just y plus p, right? So then technically, by the Pythagorean theorem, we would just get x minus x, which is 0 squared, plus y minus negative p, or y plus p squared. And we're taking the square root of all that, right? Everybody with me? Okay, so then we could simplify that just a little bit, right? We could make this an x squared, that's just a 0, and so we end up with this equation, right? Okay, so now what am I going to do? Do I really need those square roots? No, I don't, do I? I could square both sides of this equation. Now, one thing we're going to learn this year is that when we take both sides of an equation to a power, you got to be careful with that because you can introduce extraneous solutions. And if I had a longer period today, I'd show you an example of that. But we'll see some soon enough. However, in this case, we can be a little bit lazy because we know that we're always talking about distances which are always positive, right? And so it's okay for us to do that. We know that the arguments of these square roots, whatever's inside, has to be the same, right? Because they're always going to be positive. So we could just square both sides, and we could make this even look simpler. So it ends up looking like that. Okay, everybody agree? Any ideas what we could do there? We want to try to get this thing as simplified as we can. What do you think? Just throw out some, I mean, it's just kind of, I wouldn't expect you to just know the right answer here. A lot of doing algebra and doing proofs, and this technically is a proof, right? Think what we did here, or what we're in the process of doing. We started off with just a really simple constraint on this point, and we're just going to kind of follow our nose here and see where it goes, right? We're just going to set these distances equal to each other and see if we can come up with some convenient formula or an equation. Yes?
I'm confused.
About what?
Since everything's squared, and then there was like a little square root over it.
No, it doesn't, because remember, the square root of a squared minus b squared, for example, is not equal to a minus b. It doesn't work that way, right? Okay, it doesn't work that way. You can't distribute a power over a sum or a difference, and that's what you'd be. If you tried to do that, that's what you'd be attempting to do. A square root is really a 1/2 power. So I could say, let me just. This is worth spending just a second on, because I think this is a real common source of confusion.
That was messed up.
No, it's good. That was good. That's a good question. So if you have something like the square root of a squared minus b squared, for example, that's the same thing as a squared minus b squared to the 1/2. We'll talk more about that later. But that's, you guys can see that. You can understand that, I'm sure. So then I can't do this, though. I can't distribute that to both parts. That's not the case. I could do this. Now, if I have something like a squared times b squared to the 1/2, if that's a product, I can. That's fine. But I can't distribute it when I'm adding or subtracting, right? Because what is a squared minus b squared? A squared minus b squared equals a plus b times a minus b, not a minus b quantity squared. Okay? So long story short, can't do that. Okay? Everybody okay with where we are right there? Okay, well then I want you to be. So let's go back and maybe that was a bad detour to take, bad timing. So all this is, right? This is just the distance formula applied to that segment right there, right? It's just the square root of, if you want to think of it as, if we really want to fall back on the distance formula, that's fine, right? The distance formula is just the square root of x2 minus x1 squared plus y2 minus y1 squared, right? Well, in this case, this is just going to be x1, y1, and this is just x2, y2. I just plugged them in, right? Okay, so that's this distance right here. This guy right here is just this distance, and they have to be the same, where this is x1, y1, and that's x2, y2, right?
That's the bottom one. Sorry. That's simplified.
Okay, right, so what's this one right here? This is just when we squared both sides.
Okay.
So this is just applying the straight distance formula or the Pythagorean theorem. This is simplifying a little bit because x minus 0 is just x, right? And x minus x is 0, right? So just making some minor, you're simplifying the things inside the square roots. And then this is what we get if we remove the square roots by squaring both sides. Okay? This is good. You got it. We haven't, we don't do enough of this, I think, in Algebra 2, and our curriculum in Algebra 2. We don't do enough proof. Proof is important in that. Okay, to be able to follow just a logical sequence of steps. Okay, but now we're to here. We got to do some algebra. What are some things we could maybe do?
Distribute squares.
Okay, we can't distribute, but I think by distribute the squares you mean multiply it out, expand it out. Okay, that's a good idea. And you might look ahead, and doing proof is a lot like kind of like playing a game where you got to look ahead a couple steps. Why might that be a good idea? If I were to square this out and square this out, you think there's going to be some common terms on both sides that we could subtract away? Yeah, for sure. You're going to get a y squared for one thing, right? Those are going to go away. And at the end, when I FOIL this out, I'm going to probably get a p squared and a p squared that are going to go. Some stuff's going to cancel then. That's good, right? So let's try that. If we expand out both sides, here's what we get on this side. And really, this stuff right here just became that when I expanded it out. Okay? And this stuff in the green bubble became that. And we can see there, yeah, there is some stuff that cancels. I could subtract y squared from both sides. I could subtract p squared from both sides. And if I do that, I end up with something much, much simpler. What's the last thing I could do there? Yeah, good. I could maybe add 2py to both sides. And look what I come up with. That's pretty simple, right? That's kind of cool. So we end up with a relatively small equation that describes the set of all these points, x, y, that are equidistant from the focus in the directrix. Okay? Now, could we make this even more general, do you think? What did we do here by our choice of location in the xy plane that maybe made this and pinned it down so it's maybe a little bit specific? We'd like to make this completely general if we can. Say it again. Well, what was our, where we chose to locate this, we sort of painted ourselves into a corner a little bit. It's still a good equation, but we chose to do this in such a way that the vertex of the parabola, right, sort of the point of the parabola, so to speak, was where? Was at 0, 0? Yeah. What if we did this instead, maybe more generally, so it could be any place? Well, could we take our result that we had and translate this just randomly? Instead of centering this thing on 0, 0, let's just center it on HK, where H is the x coordinate of the vertex and K is the y coordinate, and they could be anything. How do I do that? How do I take something like this, right, and we have this parabola. How do I take something and slide it by H horizontally and by K vertically? How do I do those transformations? What does the x become if I move it to the left by H? The x gets replaced with a what? How does that work? We've done this a bunch. All this stuff that we did in the past with absolute value functions. Remember when we went through that whole section on transformations? And we said we had this parent function, right? If we have a parent function that looks like f of x, then we can transform that in a bunch of ways. We could say that g of x is equal to, if I want to stretch it vertically, what did I do? I multiplied by a, right? And then what if I wanted to slide it to the left, what did I do? X minus h. Okay, good. And then if I wanted to move it up vertically, what would I do? I'm going to add k. But this is really just a y, isn't it? Right? G of x was just a fancy name for y. So if I had y equals a times f of x minus h plus k, what if I just subtracted k from both sides? Then I would have gotten y minus k equals a times f of x minus h. Okay, so what do we find there? If I want to slide this thing horizontally, I can just move it. All I have to do is subtract an h from it. H represents the coordinate of where I end up, the x coordinate of where I end up, right? If I want to slide it vertically, I can either add k to this side, or maybe more easily, I could just subtract k from this side, right? So that's always going to work. If I want to slide things horizontally and vertically, all I've got to do is replace the x with an x minus h, and the y with, what did I just do? And the y with a y minus k, right? And if I do that, then I end up with a new equation that represents everything. That's all possible parabolas that we could draw, right? Where the vertex is at hk, and p is just defined as that distance, the distance between the focus and the vertex, right? 2p would define the distance between the focus and the directrix. Okay? Does that make sense? All I want you to get today, I don't want you to be able to do any algebra. I just want you to be able to kind of see how we built that equation. Right?
See you guys.
Go back where? Oh!
The one you translate HK. Yeah.
So, that one?
You have to go back to the bottom. After you move.
That one?
Yeah.
That one, okay.